chemical kinetics. Kinetics simply means speed. So here we are interested in figuring out what is the speed of a reaction, how can we calculate it, what are some of the factors that control it. So speed of a reaction, we also use a very common term called the rate of a reaction. Rate, essentially, remember, means speed. How can we measure speed of a reaction? There are two ways we can measure speed of a reaction or rate of a reaction or reaction rate, which is by measuring the change in concentration of the reactant or change in concentration of product per unit time. This is, for example, if I'm looking at a reaction where A is converting into B, I can figure out that at time 0, which means initially my concentration of A is, let's say, 10.0 moles. After 10 seconds have passed, at 10 seconds my concentration of A is 2.0 moles, which means how much has the concentration of A changed? The concentration of A changed by 8 over a period of 10 seconds. So 8 divided by 10 seconds, that would give me my speed of a reaction, which means my speed would always have a unit of molarity over time. Molarity can be molar, micromolar, millimolar, whatever you want, and time could be seconds, minutes, hours. So this is usually the speed of a reaction. We can figure it out by measuring the rate of disappearance of A. Why? Because A is a reactant. Reactant will always disappear. Or we can also measure it by measuring the amount of product that is being created. So rate of appearance of product. So these are called as disappearance of reactant or the rate of appearance of a product, because concentration of product is increasing over time. There are some factors that would affect the rate of the reaction that control it. Let's look at those factors real quick. The first is size of your reactant. So for example, usually it is more important in case of solid reactant. So for example, if I take this solid and I want to react it with this liquid in beaker. Okay, one is I just put this solid directly in here. The other way is I can ground up the solid into really small pieces and then I can add it into my beaker. The speed of the reaction in the latter part would be faster. Why? Because by grinding up my solid, I have increased the surface area for the reaction between the two reactants. The area of contact has increased. The next factor is concentration of reactant, which simply means that if you have more reactant, that means there will be a faster reaction. Why? Because remember, for any reaction to occur, the two reactants, if I have two molecules of reactants, they need to collide with each other. They need to come together, collide, and whenever this collision meets all the requirements, there are several requirements that this collision needs to meet in order to be able to produce products. So if there is more higher concentration, that means I have more amount of molecules in less amount of space. That is concentration, right? More solute in less amount of solvent. So higher the concentration, that simply means you have a lot of molecules in a small space, which means there's more chances of them colliding with each other, which can increase the speed of the reaction. The next factor is temperature. If you increase the temperature, usually increasing the temperature increases the reaction rate. Why? Because when we increase the temperature, we add heat into the system. Heat means we are increasing kinetic energy of the molecules. If you increase kinetic energy, that means molecules will be in more motion. Higher the motion means there are more chances of these particles colliding with each other. And more collision means faster would be the rate of the reaction. The next factor is nature of the reactant. That simply means some reactants are more reactive in comparison to other. For example, if I take sodium, I put this in water and I compare it to copper, and I take a block of copper, put it in water. Sodium will react almost instantaneously, very aggressively. Why? Because that's because that is the property of sodium. It just reacts very fast. Okay, so that's nature of reactant. The last factor is presence of catalyst. By definition, catalyst is simply a substance that can increase the speed of reaction. That is just the what is the definition of a catalyst. Okay, so that just means if you have a catalyst present, it will increase the speed of the reaction. How and why, we'll talk about that later on. For example, this slide is showing you that sufficient collision energy is required for a reaction to occur, which simply means this is one of the factors for the collisions to produce product. So whenever the molecules are reacting with each other, first thing that they do is they come in contact with each other, they collide with each other. Sometimes these collisions are very high in energy. Okay, when I say high, high is a very relative term, so it has to be greater than the threshold energy. So there's always a threshold value. As long as this collision is happening at an energy greater than this threshold, it is going to produce products. Whereas if no reaction can occur if the collision energy is too low. So they need to collide. First thing, they need to collide at a higher energy than the threshold value. Only then they will produce products. Now let's look at what is the expression for rate of a reaction. The rate of a reaction, like we said, is measured by monitoring the change in concentration of reactant or product over time. So usually it is molarity over time. Seconds, hours, minutes, doesn't matter. So if we are looking at a reaction, for example, if I focus on A is changing into B, I can monitor the change in concentration of A, meaning I'll measure what is the initial concentration of A, what is the final concentration of A1, A2. I can find the change in concentration and will take the time, how long did it take for this concentration to change, and you take the ratio. So A2 minus A1 divided by T2 minus T1. Initial time, initial concentration, final concentration. So usually in chemistry, we write it as this format. Delta here stands for change. Change means final minus initial. Whenever you see this symbol, delta, meaning a small triangle, it's called delta. That means we are talking about change in concentration. Final minus initial, always. Final minus initial. You cannot do reverse. Final minus initial. And whenever we see these symbols in chemistry, square parentheses, that means we are talking about concentration. So remember this, whenever I put square parentheses around anything, that means I'm talking about concentration of that substance. So in this case, your rate will be change in concentration of A over change in time. And because A is my reactant, the concentration of A is decreasing over time. And it is final minus initial, so that would always be a negative term. But speed can never be a negative term, so that's why we put a negative sign here to make it positive. So remember, speed is always going to be a positive term, right? Because even if your car is reversing at 10 miles per hour, you don't say it's negative 10 miles per hour. The speed is 10 miles per hour, right? So same thing here. Even if the concentration of A is decreasing, the speed will always be a positive term. And that's why we put a negative here to make your speed positive. So rate of disappearance of reactant would always have a negative sign in front of it. Whereas if we are talking about rate of formation of a product, it will always have a positive sign because your product concentration is increasing over time. So it would be change in concentration of B over change in time. And this would always be a positive sign. So in general, stoichiometry plays a very important role here when we are writing the reaction rate. Stoichiometry mean this coefficient A, B, B, C, D, D, right? So these coefficients are included in your reaction rate. For example, if I'm interested in speed of reaction with respect to A is my reactant, it would be negative change in concentration of A over change in time and divided by the coefficient. So it would be divided by A. If I'm interested in C, that would be change in concentration of C, sorry, not negative because it's a product, so it would be positive change in concentration of C over change in time and divided by the stoichiometric coefficient, which is C. What does that mean? For example, let's take a look at a chemical reaction. N2 plus 3H2 gives you 2NH3. From stoichiometry, you might remember that for this reaction, for every 1 mole of nitrogen, we need 3 moles of hydrogen, which means when you lose 1 mole of hydrogen, you are also losing 3 moles of hydrogen at that time, which means hydrogen is disappearing 3 times faster than nitrogen. Why? Because nitrogen you only use 1 mole, whereas for hydrogen you end up using 3 moles. So you're using 3 times the amount, so it disappears 3 times faster. So that is the relationship that we get in speed of reaction as well. So these coefficients can help you with the speed of reaction when you're comparing the reactants and products. So the best way to write these relationships is you write one reactant at a time. So if I'm interested in nitrogen, speed of reaction will be change in nitrogen over change in time, negative, and this would be divided by 1 because the coefficient is 1, is equal to change in concentration of hydrogen, negative because it's a reactant, over change in time divided by 3, equals ammonia is a product, so change in concentration of ammonia over change in time divided by 2. So these are the relationships between all of them. This is rate of disappearance of nitrogen, this is rate of disappearance of hydrogen, this is rate of disappearance of ammonia, and these coefficients that you see 1:3, 1:2, these are just helping you relate them to each other. Okay, so if I know hydrogen rate, then I can figure out what is nitrogen. Just take the hydrogen divided by 3, that is the rate of nitrogen. Okay, so these relationships just can help you figure out the rate with respect to one or the other reactant. Another example is H2 plus I2 gives you 2HI, which means if I find negative of this change in concentration right here equals negative of I2 change in concentration, everything is divided by 1 because the coefficients you can see here, nothing is written, that means it's 1, nothing is written, that means it's 1, and here HI is twice, so it would be 1/2. Questions could be like this. For example, for this reaction, 2 hydrogen plus oxygen gives you 2 water molecules. Express the reaction rate in terms of changes of hydrogen, oxygen and water with time. So if I write the reaction rate, that simply means change in concentration of H2 over time negative, and this would be divided by 2, is equal to negative change in concentration of O2 over time divided by 1 because the coefficient is 1, which is also equal to positive change in concentration of water divided by change in time divided by 2. So those are your relationship between all of them. This is not a negative sign. Okay, so these are all the reaction and all of them are same. Basically, if you take this divide by 2, it is going to give you the same rate as this and same rate as this divided by 2. So the rate speed of reaction is going to be one speed, right? So if your car is running at 10 miles per hour, all your 4 tires are running at 10 miles per hour, right? So the speed of the reaction is 1. It's just that with respect to each of your reactant, it's a different one. Okay, when oxygen is decreasing, so I can give you just question A as one question, or I can give you question B as one question. Okay, it can be a separate question. When concentration of oxygen is decreasing at 0.23 moles per liter per second, at what rate is concentration of water increasing? So if oxygen is going down at 0.23 molar per second, the question is asking at what rate is water disappearing. One is, you can do this mathematically, I'll show you, but another thing is you can think about this in your head. If oxygen is going at 0.23, water should be going twice that rate. Why? Because if for every 1 mole of oxygen you end up using 2 moles of water, so water is disappearing twice that rate. So your answer basically is 0.46 molar per second. If you want to use the math, you can write the relationship. What is the relationship? Change in concentration of O2 over change in time for oxygen, which is negative, is equal to change in concentration of water over change in time divided by 2, right? So the question tells you this value is 0.23, and it's asking you what is this change in concentration of water. So what is this? I need to isolate change in concentration of water, so I need to get rid of this 2, which means I multiply this by 2, and that would cancel this out, which means I would also multiply this by 2, which means you take this, multiply this by 2, and you're left with change in concentration of water over time. And that's what the question is asking, which is 0.23 times 2 again. So either or, whatever works for you, you can use that approach. Right here, if I'm interested at 50 seconds instantaneous rate, we go around 50 seconds. This point, I'll draw this tangent right here, plus minus 10 seconds around it, and we will find the slope of the graph. You do not have to do this, and there wouldn't be a question like this to find it, but you should just know what's the difference between the two. Okay, instantaneous rate just means at this given point. If I'm taking the average rate, that would be at this time times 0, at this time, which is like 90 seconds. What is the change? This was 1.7 or 1.6, this was 0. That would give you the average around the whole time. But instantaneous means at this time what it was, at this time what it was. And the third one is called the initial rate. A lot of times when we are doing experiments and we are interested in figuring out kinetic parameters for a given reaction, usually the reaction rate we find is the initial rate. Why? Because your rate continuously changes during the reaction. For example, your car, if you're running it, when you push the accelerator, in the beginning it goes slow, and it keeps on increasing, right? Similarly, in case of reaction, it's not a fixed rate. Your rate of the reaction changes because your concentration of reactants are continuously changing. Meaning, in the beginning of the reaction, when time was 0, around 0 time, in the very beginning, your reactants are a lot. You have a lot of reactants, so the rate is very high, the speed of the reaction is very high. As time progresses, the speed of the reaction decreases slowly. Why? Because you're reducing the amount of reactants present, and the concentration of reactant controls the speed of the reaction. So if it is less, the speed will also be reducing. Okay, so that's why we find initial rate. If I'm interested in a rate, I will find the initial, in the very beginning, what's the rate. Then I'm interested in at another time, then I will start the reaction at that time at that concentration, and I'll find what is the initial rate at that time. So those are different ways or different types of rates that we can find. For example, like this, use the concentration and time data for the reaction A to B to determine the average rate between 10 seconds and 30 seconds. So I just need average, which means 10 seconds is this, 30 seconds is this. So final concentration 0.0650 minus initial concentration 0.0295 molar divided by change in time, which is 30.0 minus 10.0. Just take the ratio, plug those in, and that would be your rate, average rate around this time. So average you can find just by subtracting, but if you want instant, you need to make a graph.